Welcome to the NAWCC online learning series. My name is Jerry Kiefer and I will be your instructor. This instruction will cover the installation of bushings and depthing on a milling machine. We will also cover other various related procedures. The first topic will be a brief discussion on bushing in general. Most mechanical horological movements are powered by a weight or a spring. As wheels, arbors, and pivots rotate for many years, they can wear a path in the movement as seen in this example where I'm moving the wheel and the pivot is moving. When this happens, the wheel teeth and pinion teeth no longer properly mesh, causing an increase in friction. This in turn can cause a movement to malfunction. The traditional way to correct this has been to attempt to drill or ream a hole centered on the original pivot location, as can be seen on this movement where the hole is much larger than the actual pivot. If a correctly fitted bushing is friction fitted to the hole, as can be seen in this case, the pivot will then be returned to its original position and proper function. While there are many methods of bushing, most who are serious about repair eventually move to a bushing machine. While the milling machine bushing procedure is similar to a bushing machine, it offers far greater versatility and accuracy, as we will see later in this course. The next topic will be on the tools required to bush with a bushing machine. While other mills are available, this particular Shermine mill will be used to demonstrate the bushing procedure because of its capability, versatility, and accuracy. In addition, it is compatible in size and cost to a typical bushing machine. While a bushing machine is limited to bushing, a mill along with a compatible lathe will allow a repair person to machine any required repair part as well as build a movement from bar stock. In addition, it eliminates the need for many other specialized tools with the exception of possibly a mainspring winder. When purchasing a milling machine for bushing, one additional item that is required will be blocks that will support a movement plate as shown in this example. In addition to the blocks to hold the plate under the mill, you would also need a support that goes under the movement plate to hold it when doing the bushing procedure. Because you have purchased a milling machine, you can machine the blocks that are required to hold the movement plate from bar stock, or in this case, they can be purchased from Sherline by request. When bushing, you will need to purchase bushing reamers, whether it be for a milling machine, bushing machine, or what other method you may use. In this case, we are showing a complete set of reamers and stumps and locating devices. However, from the supply houses, you can purchase individual reamers so that you would not have to purchase a complete set if you did not want to. In addition to purchasing reamers so that you can ream a hole that will properly fit a bushing, you can also purchase a step block that will fit under various raised bridges and allow you to support the bridge when bushing. The next topic will be actually bushing on the milling machine. So far, I have mounted the movement plate blocks on the mill, as can be seen, and I have actually installed a movement plate in the blocks, and they have been clamped in, as you can see the screws holding. In order to find the center of a bushing hole, there are typically three methods that can be used with a milling machine. The first method we're going to look at is actually a centering cone that is typically used with a milling machine and can be purchased from any of the clock and watch supply houses. And it has a point on the end. And because with the milling machine has hand wheels that will allow the plate to be moved in any different direction, I will first take the point of the cone and move it down close to the bushing hole. From that point, I can take a magnifier and I can center the point on the hole of the original location of the bushing, or the original location of the pivot, rather. And once that has been completed, then I'm ready to remove the cone and put in a reamer to do the bushing. However, before we ream the hole for the bushing, we're going to show two other methods that we can use to locate the hole. Previously, we have just looked at a method of locating the spindle over the original pivot hole by using a cone. I have now installed a bushing reamer in the spindle, which I could actually go ahead and ream the hole. However, I want to show another method of centering the reamer over the hole utilizing the reamer itself. And once you become familiar with the whole process, you may be able to use this method. What we can see is that the reamer is half round, and I'm now going to remove the reamer from the mill and do a further explanation of how we would use that to locate the center hole of the pivot. On the board, we can see that I have drawn a typical, this would be an extreme example of how a pivot may wear a hole from its original location, which may be in this area, all the way over to an area in here. Okay, in this particular case, even though it's extreme, what we need to do is we need to locate the hole that we're going to do for the bushing would need to be located in the original pivot hole, which would be on this dotted line. And because our reamer is half round, from the top here, we can take the flat side under magnification and locate it to the center of the original pivot hole. Once we do that, we can turn the reamer 90 degrees and do another location to make sure it's in the center of the hole in the opposite direction, 90 degrees away. Then the reamer will be in the center of the original pivot hole. You will only use this method when you become very comfortable using reamers, a milling machine, or however you're going to bush, and you're comfortable that this system will actually do the job for you. The third method that we're going to look at, and is actually the most accurate method of locating the original pivot hole, what I have done here is in the drill chuck I have installed actually a drill shank. We can use drill shanks, we can use a pin, we can use gauge pins, but we need something the same size as the original pivot on the arbor. And what we do with this is, again, we have the ability to move this around, the bed around on the milling machine. What I'm going to do is I'm going to position the pin so it will just drop into the original pivot hole under magnification. In this particular case, once I get this in, I'll give you a little further explanation here. I have now positioned it so it now drops into the original hole in the area in which we're going to bush. And so we have actually located this in the exact position. So at this point, we're now ready to install the reamer in the chuck and go ahead and ream this hole for installing a bushing. Okay, we have now located the spindle directly over the pivot hole that we want to ream. And the reamer has been installed in the mill. But before we go ahead and ream this, I want to have a little more of an explanation of what's going on here. One of the versatility parts of the milling machine is the fact that it has a variable speed drive, which is very important in this case. Normally, we would not use a drill chuck for reaming holes for the simple reason that the drill chuck will sometimes have run out, and the machines that operate the drill chuck, such as drill presses and so on, will also have some run out. And when you have run out and you operate the reamers at a very high speed, they will tend to open up the hole so that you will not get a proper friction fit on the bushing. However, with this particular milling machine, which has a variable speed drive, we can slow the chuck down to a very slow speed when we do the reaming, which will give us a very accurately reamed hole. And in addition, because of the beds are locked in place on the milling machine, it will be very accurately positioned, and you will be assured that the hole will be in the position it's supposed to be in. And because the reamer is turned at a very slow speed, it will have a very accurately sized hole, so we have proper fitting of the bushing. We will next go ahead and turn the milling machine on and go ahead and ream for the bushing that we're going to install in this plate. We have now reamed the hole, and I have went ahead and I have set a bushing on top of the hole that we have reamed. From this point, I'm going to close the chuck, and I'm going to drop the chuck down on top of the bushing. Okay, we have now set the chuck, the tip of the chuck, over the bushing, and we're going to take a hammer on top up here and tap the top of the drawbar bolt, which will seat the bushing. If you'll notice that when we did this, there was a spring. The drawbar is an extra length drawbar with a spring on it. And the reason for that is it allows us to tap the top of that and drive the bushing in. This part of it is included with the blocks, the movement plate blocks that are shown right here from Shoreline when you order the blocks. Okay, we now have the plate that we just bushed. And as you can see, I'm looking at the bottom of the plate, and you can see the bushing that has been installed from the bottom. If I were installing a bushing that has the exact size hole for the pivot, I usually check the hole of the pivot with a magnifier. And what I'm looking for is any burrs or anything that's in the way, and I'm also running my finger over the top of the bushing to make sure that it is flush with the bottom of the plate. Okay, once I've done that, if I did have a burr, for removing burrs, I prefer to use a 4-flute ball end mill that is available from any of the machine tool supply houses. And the reason I prefer the 4-flute ball end mill is the 4 flutes give a really nice finish, and they are also extremely sharp and work very well for this type of an application. If I was going to deburr the hole, if it required it, I would just set the end of the ball in, give it about 1 turn, a very light pressure, and what would happen is I would deburr the end of that bushing to the point where it is ready to go ahead and use. When I flip the plate over, if I needed to have an oil sink installed in the bushing, I would use the same 4-flute end mill. And I prefer the ball end mill as opposed to the tapered burrs that are commonly used to make an oil sink. And when we do the oil sink, I would set it over the hole. I would use light pressure, give it 2 or 3 back and forth spins, and it applies a very nice oil sink that is very similar to what it was installed by the original manufacturer. Okay, I would like to give a further explanation on using the ball end mill to do an oil sink and why I prefer that ball end mill. If I'm using a tapered reamer or tapered burr, I end up with a tapered area so in effect I am removing a tapered area in the plate to act as an oil sink. In doing this, I am typically reducing the area where the pivot rides in the plate from here to here. However, when I do the ball end mill, what I end up with is a very gentle curvature at the top, which increases the area that the pivot has to ride in the plate, but yet offers the wider section and gentle half-moon curvature that supplies as an oil, that will supply the oil sink as well as a very tapered oil sink. But in this case, I am increasing the width of the area that the pivot will actually ride in. When I'm talking about these end mills, my personal preference in sizes is 3/16 inch, 1/8 inch, and 1/16 inch, which covers most of the oil sinks and chamfering areas that I need to do in clocks. We now have the plate with the bushing installed, and in some cases we will install the bushing where the bushing hole is the proper size for the pivot. However, if it's not the proper size for the pivot, then we may have to enlarge that hole. The traditional method of enlarging that hole is to use a tapered reamer that is inserted from the back side, typically from the back side of the plate, and we ream the hole to the size that we would like to have for the pivot. Once this is completed, then we would go ahead and assemble the movement and check and make sure everything is functioning correctly. However, personally, when we're reaming with a tapered reamer, I prefer to have the bushing hole to be straight and non-tapered as it was supplied from the original manufacturer. So my method of enlarging and sizing the bushing hole is to take a gauge pin and to sharpen the tip at about 12 degrees. And in operation, what I do is I take the movement and I assemble it similar to what we see here, and I enter from the opposite plate of where the bushing that I'm trying to enlarge is, and I go from the back side, ream from the back side all the way through the hole. And what this does is it provides a square, straight hole in the bushing, as well as lining up the hole so it's perfectly parallel with the arbor when it's installed in the movement plate. In addition, as I turn this now, you'll be able to see that flat spot that was ground at the 12 degrees on the gauge pin. I have just demonstrated the use of a gauge pin by grinding the end to make a reamer to size the bushing. While some of you may not be familiar with gauge pins, they are utilized in the machine tool industry and are available from any machine tool supplier. What we're showing here is a complete set of gauge pins, and when you buy these sets, they come in 1/1000th increments, and what this allows you to do is to grind these so you have a multiple number of reamers and you can ream to the exact desired size. However, you do not need to buy a complete set because most of the machine tool supply houses will also sell them individually. And in most cases, they are less costly than a good quality set of tapered reamers. Our next topic will be high precision bushing. From time to time, you're going to need to bush in areas that are very close to the edge of the plate or need to be done in a very precision manner. The first explanation I want to show is a typical reamer. So typically for installing bushings in a plate, we're going to use a reamer. As you can see, this reamer, this is a large reamer for explanation purposes. You can see the reamer is half round, as we've already discussed. But what happens when the reamer turns and it goes to ream out the plate, because the cutting edges are on the side, they are pushing out from the reamer in both directions. And this can be a problem, as we're going to discuss here shortly. Having just explained the reamer, I wanted to further explain what happens up on the board. From time to time, we will run into a pivot hole that is extremely close to the edge of the plate. And in this situation, if we go in and we ream this particular hole with a bushing reamer, because the bushing reamer is forcing metal out from the side, we will sometimes bulge the metal out on the side of the plate and cause all kinds of issues. One of the ways that we can tackle this, because we're using a milling machine that is very precisely holding the plate in the exact locations, and we can very finely adjust what we're doing, is that we can come in and rather than ream a hole directly in the middle of where the pivot hole is, we can ream a larger hole that is offset from where the pivot hole is. Okay, like this. So if we put a blank in an area like this, then we can come back and drill the hole, the pivot hole, in the exact location it was. And one of the reasons we can get back to that exact location is before we machine this hole, we can set the hand wheels at 0 on the milling machine that will allow us to come back to that exact location. Once we've set those hand wheels, then rather than using a reamer to do this larger hole, we can use an end mill. And I'll further explain this here a little later, but an end mill will center cut on the plate, but in addition, it will not push the metal out to the side. It has cutters on the side that has no force on the side of the metal. So therefore, we can very precisely control where the edge of that end mill is and not risk any damage to the end of the plate. To further explain an end mill, I'm showing an example here. And an end mill, for those who may not be familiar with them, are very similar to a drill bit. However, they have a flat end, and they have 2 cutting surfaces or 4 cutting surfaces, or whatever number of flutes it will be. So it can cut going in similar to a drill bit, as well as it has cutting edges on the side that will machine on the side. Therefore, when it goes straight into a piece of metal, or in fact in this case a clock plate, it will not force any metal out to the sides. Therefore, it can be very precisionally located on the edge of a plate without affecting, without damaging the side of the plate if you decide to machine a hole straight down through that plate. We are now set up with a movement plate in place that has a pivot hole right at the very, very edge of the plate that you may encounter from time to time. The end mill, or I shouldn't say the end mill, I have already centered the spindle on the pivot hole and set my hand wheels to 0 so I can come back to that position. I have now located the end mill right up next, one of the cutting edges, right up next to the edge of the plate, and I'm going to go ahead and machine a hole through the plate that will be offset from the hole as I explained on the board. I'm now going to turn the mill on to start the milling process. However, when using an end mill, I use a much faster speed than I do if I'm using a reamer, because I don't have the effect of moving metal out from the side. As you can see, the end mill does a very nice job of controlled machining without damaging the end or affecting the edge of the plate, but yet being only a few thousandths from the edge of the plate. Okay, I have now placed a bushing over the hole that we just machined with the end mill. Because I have the collet system in place, I'm going to drop a rod down through the center of the drawbar, which is going to seat on top of the bushing, and I'm going to take the hammer and I'm going to tap it into place. And now the bushing is completely seated in the movement plate. Okay, we have now ready to drill the hole. We've put the blank bushing in place at the edge of the plate, and we're ready to drill the hole. And so what I'm going to do, the first thing I'm going to do is I'm going to reposition the hand wheels on the mill to bring the location of the spindle directly over the original hole that was set up before I did the machining with the end mill. Now that I have that in place, I'm going to lock my slide, I'm going to turn on my mill, and I'm going to spot the location. I have now installed a drill bit in the spindle, and since the spindle has been relocated in the original position of the pivot hole, when I drill this hole in the blank, it will now be in its original position. I am now showing the plate as it has been removed from the milling machine, showing the offset bushing with the hole drilled in the original location to the original or to the size that is required for the pivot. Okay, what I've done now is I have tipped the plate over to show the bottom of the bushing. And I have a file in my hand because occasionally from time to time the bushings may not be the right height for the plate, or you may want to dress the bushing flush with the plate, especially on the back side. However, when using a file to do this, the edge of the file will usually dig into the plate and cause scratches in the plate. In this particular case, I have taken a fine file and I've polished the edges round so that it would not ever dig into a plate. In this case, I can take the file and I can move it over the plate and I can dress the bushing flush with the plate without putting any scratches into the plate itself. As part of precision bushing, on the milling machine, it is precise enough to allow you to actually bush watch plates. Now, watch plates typically are jeweled and we don't run into too much bushing on this. However, in clock repair, we may look at a platform escapement, or you may get in a job where you have an inexpensive 7-jewel Elgin pocket watch, for example, that has sentimental value that somebody says, well, I really need to have this thing repaired. And a bushing would help the running operation. Other uses for this would be when you're working with 200, 250-year-old Fusee watches that are also very valuable. And some of those were quite low jeweled in some cases, and you may want to bush those in order to get them to run properly. What I have done here is I have set up and I have put a chuck on the bed of the mill, and I have put a watch plate in here. And in the spindle, I have machined a pivot point that is identical to the size of the pivot that we're going to rebush in this clock plate, or in this watch plate rather. I have now installed an end mill in the spindle that is located in the exact, or is located center to the original pivot that I had located with the previous item that was in the spindle. So what I'm going to do now is I'm going to turn the milling machine on. I'm going to lower the end mill, and we are going to machine the hole for the bushing in this watch plate. After machining the hole, I have now placed a bushing over the hole that was just machined. I have taken a flat-ended staking tool stake and put it into the spindle of the mill. Because of the small size of the bushing that is going into the hole, it is somewhere in the area of about 40 thousandths or 1 millimeter. Because of the size and because of the thickness of the watch plate, we really do not need to have support on the back side of the watch plate. And we do not need to tap this bushing in place because it can be driven in with the Z-axis of the milling machine. So at this point, I'm going to lower the staking punch that's mounted in the spindle and just easily push the bushing into place. The next topic that we're going to talk about will be depthing. From time to time, you may get a movement either by yourself or by another work repair person where if they install a bushing in a plate, say, for example, it would be in the position here where we have the arrow on the plate, it would be out of position where the teeth would not properly mesh and the movement probably would not operate correctly. The traditional method of dealing with this problem would be to remove the old bushing and to install a blank in the hole that where the bushing was improperly located. From that point, we would use a depthing tool, which we are showing here. So in other words, the wheel before the problem arbor and the arbor itself that has the problem would be put into this depthing tool, and the width of the pins in the arbors are adjusted so that the two wheels mesh and run properly. When you have it into position, and it's adjusted down here at the bottom so we can adjust the width and the length of that. When they are adjusted properly, then the 2 points in front of the depthing tool are the same distance as the pivot should be on the 2 wheels. So we would take that tool and put 1 point on the previous pivot hole, and we would scribe a line on the blank, we'd scribe a line on the blank bushing that we had installed. From that point, we would replace the wheels in the depthing tool with the wheel that has the problem bushing, and then the other side of the problem bushing with the next wheel, and we would come along and we would scribe that, which in turn would give an intersecting scribe marks on the plate, which we could use as a reference point as to where the pivot hole should actually be. I have previously discussed the traditional method of depthing on a movement that is typically traditionally used. However, if you have a milling machine that you're utilizing for bushing, it becomes a very simple process to use the milling machine as a depthing tool. In this case, what I have done is that I have removed a bushing that was in the improper place in the middle here as I'm pointing with my finger. And what I'm doing now is in addition to this arbor, I have installed the arbor before it and installed the arbor after it. In the spindle of the milling machine, I have placed a staking tool stake with a hole in it that is the same size as the pivot that I'm trying to locate here. And I can use anything that has a hole in it the size of the pivot. Another example would be pivot wire that you can purchase from any of the supply houses. And again, most people I think that are into bushing may also have a staking tool set where you can find a staking punch that will work as an item that we can drop. When we lower the spindle, we can drop it over the pivot. Okay, just like I've done. Now, since we've dropped that over the pivot, what we can do is we can reposition with our hand wheels the proper depthing of the wheels until they spin very freely. In this case, I'm going to drop it down just a little further to tighten it up. And now I feel that it is, by moving these back and forth one direction or the other, I can reposition that until I get a very smooth operation. All I need to do at this point now is to raise this stake that engaged the wheel that had the poorly placed bushing. I removed the nut from the top of the plate and remove the next nut, and what will happen is that the bottom plate will fall out the bottom, leaving the hole at the top exposed. All I need to do now to put this back into proper operation is to replace the stake that I have in the spindle with the next size larger reamer, bushing reamer. Go ahead and ream it because the milling machine is holding it in the exact location it should be reamed. And I'm ready to reassemble the movement, and it's all ready to go. The next topic will be about turning on the milling machine. If by chance you purchased a milling machine to do bushing but do not have a lathe, you can actually utilize the milling machine, because this particular milling machine is very versatile, as earlier mentioned. We can actually use it to do turning as we would do in a lathe. In this particular case, what I have done is I have rotated the headstock on this 90 degrees so that the spindle is actually in the vertical position. And then what I have done is I have taken the Sureline movement block, and it will allow you to clamp a regular lathe tool into the block itself, and the block can be mounted into a vise that is mounted on the bed of the mill. And in this setup, we can easily go ahead and turn bushing wire. Bushing wire looks similar to what I've got here in my hand and is available from many supply houses. The bushing wire has a hole down through the center, and we can machine a bushing to any diameter, and yet we can ream out the center hole to whatever size we'd need for a bushing. We are now going to turn the milling machine on, and we have it set up so it will act like a lathe. So as I turn this on, I can move my tool forward so it'll take a cut on the bushing wire that is installed in the spindle, and as you can see, I can also machine that to any desired size. Once I have made a pass on that, I can go ahead and measure the diameter of this, and I can adjust my hand wheels in thousandths to size that to whatever size would be required to utilize as a bushing. I have now replaced the cutting tool with a parting tool. And what I would do with this is I can move the parting tool down on what I have machined if I have it machined at the proper diameter. Once I do this, I turn the milling machine on, and as I move it forward, I will machine off a bushing at whatever length I would like to have it. And I move it forward until the bushing pops off. I don't know where the... Now that we've parted off the bushing, and it did fall down, I did pick it up, put it on the end of my finger so that you can see what it looks like next to the bushing wire that we trimmed off. I have now replaced the collet system on the milling machine with a 3-jaw chuck, and I've inserted a much larger piece of brass with a hole in it. And what I'm going to do this time is I'm going to show machining a deeper cut. And in this case, we could machine, for example, a bushing for a spring barrel. I have now installed in my movement plate block, I had drilled a hole through the back side and added an additional screw that allowed me to install a boring bar. Okay, what we're going to do with the boring bar is that a lot of times if you're making like a winding bushing or you're making a barrel bushing, you can't find a drill that will be of the proper size. By boring, you have a tool that will actually machine out the inside of a round hole to any size you want by adjusting the hand wheel. And for you people that may or may not be familiar with this, if you did purchase a Sherline mill at least, we have an instruction manual that will explain all of these procedures. From this point, what we're going to do is we're going to turn the mill on, and as I move the cutting tool inside the hole, I can bring the cutter back till I see it's starting to cut, and I can make an adjustment, and when I pass that tool inside the hole, it will enlarge that hole by a 1/2 thousandths or 10 thousandths or 20 thousandths or whatever I adjust it to do. So it is a very, very accurate way of producing a hole inside of or enlarging a hole inside of a piece of tubing. Now what we have done here so far is we have machined the outside of this, and we have shown how we can bore the inside to an exact size, and then once done we could part this off as we previously had shown. In this particular case, what we've done is we have mounted a spring barrel, a manufactured spring barrel in the chuck on the mill. And when I turn the mill on at slow speed, if I'm looking at it at the right angle, I can tell that the tooth or the gear portion of the barrel is running very true. The barrel itself is running very true. However, in this case, as you can observe, the center hole, which has never been touched, it has a wobble in it. So anytime you're working with spring barrels or have an extreme problem with a clock, you may want to check the barrel just to make sure that from the manufacturer the center hole is actually centered in the barrel. In this case it was not, and it contributed to failure of the clock. Okay, I have now and I have left the boring tool in the tool post. And what I'm going to show is how I would go in and enlarge this hole and bring it back to center in this barrel by machining it. What I'm going to do is first I'm going to turn this on so it's going very slow. And as I bring the boring tool in, you will hear an increase and decrease in cutting noise. And that just shows that the hole is not round and that the cutting action of the bit is light and heavy. So I'm going to back this out. We're going to increase the speed. I'm going to take a larger cut, and we're going to come in, and as you can see, we can bore out that hole to any size that we would like for a bushing. And in this case, we can bore it out. If we were to purchase a bushing from if we purchased a bushing from a supply house, we could bore the hole to any size within about a 1/2 thousandths of fit so that we could have a good friction fit on that bushing. Okay, what I've done now is I have a kind of an unusual spring barrel where the gear portion is separate from the barrel itself, and we're going to use this for illustration purposes. What I have done is to remove the gear from another barrel, and I put a bushing in that barrel, typically like you would in that wheel, typically like you would do in a barrel. The reason that I've done this is because if I were to try to put the boring bar into the barrel, we wouldn't be able to see what we're actually doing down in the barrel. So for this purpose, I have put the bushing in, which extends past the inside of the barrel, which is not what we would like to have. We would like to have that bushing flush with the inside of the barrel. So by using the boring bar, we can actually go in and machine off this bushing, and by turning the mill on, I can take the boring tool, and as I go across that bushing, I can machine it until it's absolutely flush with the back of the barrel itself. And I take very light cuts on this because the boring tool is extended past its really rigid stage, but it's still very accurate if we take light cuts with it. And in this case, I'm getting very close to the back of the barrel. And what I will probably do is actually just touch the barrel so that you can see what I've done. And I just touched the barrel now, and when I went across there, we can see that the bushing is flush with the back of the barrel. So we could have put this barrel into the chuck with the gear portion back, reached in and cleaned off that bushing just like we have shown here. The next topic we're going to cover is grinding verges. Now I realize that this is a far cry from bushing on a milling machine, but if you happen to buy the milling machine for bushing, it has many other purposes and is highly versatile, like I have explained earlier. And one of the things that is very important for the proper operation of a movement, especially a clock movement, is to have the proper finish on a verge. When I repair a clock personally, the most important things I have found is to bush in the proper location, properly polish the pivots, and then grind the verge. And one of the reasons I grind the verge rather than hand finish the verge is that the clock has a much stronger operation if all of the edges are very sharp, just like they came from the factory. And when you have this, you have a very clean let off of the escape wheel, and you can actually hear the difference in the sound of the clock between one that is hand, or at least one that was done by my hand, and one that I have done by grinding. Now that I've explained why I prefer to grind a verge, I have already placed a verge into the vise which is mounted to the bed of the milling machine. And what I do with this is I'm going to grind the edge of this verge to create a very sharp corner there that will allow the escape wheel to let off at a very sharp angle. In this particular case, what I did when I placed the verge in the vise, I made sure that the flat surface that I'm going to grind is parallel with the top of the vise, and that's how I retain the correct angle. Sometimes when you're mounting these, depends on what the verge looks like, it may set well above the top of the vise. And in that case, you wouldn't be able to see that it was actually parallel with the top of the vise. And so what I would use would be a parallel set that is, of course, can be purchased from any machine tool supply house. And what the parallel set is, it's paralleled pieces of metal that you can lay on top of the vise that would go up, that you could match the top of the angle of the pallet that you're trying to grind, or the verge surface. Parallels are typically used in machining when you are trying to put something in a vise and you're trying to raise it up inside the vise and hold it level. They would sit underneath the the workpiece that you're clamping on. In this case, we have the verge now mounted, and our next operation will be to actually grind the verge. We have now mounted the verge in the vise, and we've repositioned the stone so it's directly above the surface that I want to grind. Okay, since I've got this into position, you can see where the edge of the verge is. I'm going to turn the hand wheel until the verge itself, or the surface that I want to grind, is directly underneath the stone. At this point, I'm going to turn on the mill at maximum speed, and I'm going to lower the Z-axis until I hear the stone just touch the verge. Now that it has touched the verge, I'm going to run it across, back and forth, and that is generally all that a verge will require for surfacing. Now that I've removed the verge from the vise, you can see that the surface is very smooth and very sharp. If it were a surface that the escape wheel was going to go over, it would be this particular surface would not need to be touched beyond this grinding. When you mount the verge into the vise, there are many different surfaces that you may grind, and in most cases it can be positioned and manipulated so that you can grind whatever surface you'd want to grind. I should also mention that the stone that was used in the milling machine is actually a stone that's used in a lathe grinding tool. So normally if you look in a machine tool catalog and look under tool post grinding stones, you will find small stones that could be utilized for this type of work somewhere in the 180 to 300 grit range. I would like to thank everyone for joining us at the bench today.